NVH theory, understanding where events occur in the human audio spectrum. So think of 0 to 20 kilohertz as being the human audio spectrum. In other words, as humans, what you can hear and feel. In the animation here, we have 0 to 20 hertz. You'd experience that as a vibration only. When we move up to 20 to 200 hertz, this is a little bit of a grey area because we're all different in this area. Some of us will experience a vibration, some will experience noise. We are both talking about one and the same phenomenon. Once we get above 200 hertz, generally that is noise only. So that would be maybe a transmission whine, brake squeal, that's certainly high frequency, about 4 kilohertz. Bearings, Frank, spring to mind, where you have noise or vibration, both talking about one and the same thing. We just experience them differently. So in this animation, looking at amplitude, we take away the dampers on the vehicle and then we apply a force to the tyre. We see the effects felt within the chassis. This is the bound and the rebound of the vehicle. Large force there being applied, greater amplitude affected, greater amplitude in terms of vibration felt in the chassis. Here now we reattach the dampers, so now we are taking away, we are minimising the effects of the force applied to the chassis. So you see the amplitude is reduced and the bounding and the rebounding is reduced. We are interested in how intense, that's probably the best description, how intense is a noise, how intense is a vibration? Is it a characteristic? Is it excessive?
So I think my understanding of what you're explaining there is that noise, vibration, harshness is something which we can feel through our body,
Yeah.
something which we can hear, and something which we can actually see. We may see, say, the rear view mirror in a car move, vibrate, all represents this phenomenon of a change of air pressure that our ears detect as noise.
That's exactly right. In fact, I hadn't thought of the visual side of the vibration. Think of rear view mirror or steering wheel. Mm-hmm. Steering wheel flutter, shimmy. It's a physical event that you can detect. Obviously, the way in which that steering wheel will shimmy will be at the frequency of the vibration. So that will be felt in the floor pan, in the steering wheel, in the pedal box, whatever it may be.
Would it also be true to say that if a lower frequency vibration, something which I would interpret as something that's relatively heavy, is something we're more likely to feel and maybe hear a little as well, whereas something where we see the vibration, say the rear view mirror, is more of a higher frequency with a lower mass. Is that reasonable to you?
Yeah, I think the effects of the vibration in the chassis are certainly. When we talk about vibration, it's something that we can feel. It's transmitting through the floor pan. It may be that the rear view mirror is vibrating at the same frequency as what we can feel in the floor pan. It's a visual representation of the same responding component. So here then, a tuning fork vibrating at its natural frequency of 200 hertz. Now 200 hertz falls into that area where we will hear that sound, and we can see here that we've applied a force and the frequency from the tuning fork is at 200 hertz, but more importantly the amplitude. Now here we have the tuning fork, it's been struck by a small hammer and a large hammer. Note how the amplitude has changed but the frequency remained the same. And finally, if we shorten the prongs of the tuning fork, we do change its natural frequency. You'll notice now that the frequency of the tuning fork is greater when we strike that fork with the same force.
So what we've done here in effect is we've taken a vehicle, we've put some sports suspension on it, we've lowered the suspension, and we've done exactly what that animation has just shown us. We've changed the natural frequencies at which that vehicle now will demonstrate vibration.
Yeah. The rigidity, if you like, has changed. So with the tuning fork example, the way in which that vibrates, it will now be a higher frequency. It's a stiffer, more rigid fork. Relay that to the chassis, The benefits of a stiff chassis is great driving feel, great feedback, but the downside of that is more passage of vibration or transfer of vibration into the cabin. Whilst we can't always modify or improve on that, we need to be aware of this phenomena. We need to be aware that these concerns exist, and that it's the engineers who deal with this during manufacture and design of the vehicle. It's very rare that we'll change that, but we need to be aware. Awareness is key.
You mentioned awareness. I'm mindful here that we now have vehicles which have selectable suspension settings, whereby the vehicle may be okay in one setting and produce a problem in another, and this may be something we need to take into account as well.
Yeah, certainly during the road test, during a customer interview, let's set that vehicle up exactly how the customer drives, customer settings, mode settings, sport, the active damping, ride height. All of this will affect the cabin from a noise vibration point of view.
And we also have now a higher level of technology. We have active noise control. Several manufacturers now have noise suppression systems built into the vehicle, very advanced systems, to deny the driver any experience of noise. It's actually working against us, hiding potentially a problem with the car because of the very nature of the technology equipped with the vehicle.
Like there wasn't enough variables there. We're tackling
now we've got some more.
Yeah, tackling the engineers at their own game.
Yeah.
Okay, so vibration theory. Think of the three elements of vibration. What is required for you to experience that vibration in the cabin? Take the engine, for example, the source of our vibration. We accept that the engine will vibrate. There will be noise from the engine. Think of that noise then travelling along, or that vibration travelling along the exhaust system, and the exhaust system fouling the chassis at some point. We've now got a transfer of vibration from the engine along the exhaust into the chassis. And the responder of that would be maybe the trims, the floor pan. The customer may feel the engine vibration in the pedals, in the seat. So the source being the engine, the transfer in this case would be the exhaust system, and the responder would be the trim, seat, whatever it may be. Source, transfer, responder. And the question is there, Frank, which one of those do you rectify?
I think I'm got to admit guilty here with all the experience I've had in the past dealing with noise and vibration. I think it would be fair to say that historically we've dealt with the respondent. We've dealt with the bit that's creating the noise and not actually the source or the transfer path.
Most certainly. I think using a crude example, a misfiring engine is going to have a excessive vibration. That will be felt in the cabin. Maybe the trims are now vibrating. Do we rectify the trim rattle there? Of course not. We go to the source. But that's a typical example. And coming up now, we've got an example of wheel imbalance, source, transfer, responder. Let's run the animation. Okay, so here we have imbalanced wheel. Okay, so notice how the wheel is almost thrown off its centre line there as the imbalance reaches the peak. So there is our source. That then is transferred along the suspension because it has to travel. Travels through the suspension, through the frame, and then of course into the steering column. The steering column acts like an antenna, yeah, and that is felt by the driver who is actually holding the responding component. Something I'm sure we're all familiar with. And generally in this scenario, we rectify the source of our vibration.
I think the big issue here as a technician, from my point of view, is that in order to understand the source, we're then actually preventing premature failure of components, because this energy has to be absorbed by different components, bearings, suspension, shock absorbers, and if there is an issue there, it's important we deal with the cause of the problem, therefore protecting the life of a component from premature failure.
Yeah, consequential damage.
Yes.
Yeah. Vibration theory, then looking at sound. So we talked about vibration being something that we feel, sound now something that we hear. They are one in the same. We experience them differently as humans. The animation here looks at differential pinion bearing, and look at the condition of this bearing here, how the bearing is just given, how it's collapsed slightly, and now we have movement in the pinion shaft, and how the pinion gear now and the tooth contact between pinion and crown wheel is constantly changing, and the noise generated, as you can hear, is horrendous. As of course as road speed increases, then so will the noise level. Multitude of noises to consider there. Of course we'd have a noise, a vibration maybe at P1 at prop shaft frequency. We'd have a tooth contact frequency, which we'll talk about later on in another presentation. But again, always something that you're going to hear because it is a higher frequency.
I think one of the most challenging things from a technical point of view is actually nailing a potential bearing in the process of failing. It's one of the most challenging tasks we have.
I think also trying to identify a failed or failing component within a drivetrain, that will have an offending frequency. We may have knowledge of that transmission internally. That will allow us certainly to focus on components within that transmission when we dismantle that transmission based on the frequencies that we've obtained from the microphone or the accelerometer. So vibration orders, this is something that we need to grasp to understand what a vibration order is, and it's no more than the number of disturbances per revolution of a component. So if you think about an oval wheel, for example, so 1 revolution, 2 disturbances. So here we have an imbalance. That's a classic example. So 1 disturbance per revolution of the wheel, or radial force variation, and this is where about the circumference of the tyre there is a stiff spot within the tyre. So of course when that area of the tyre reaches the road surface, we momentarily get a lift off centre of the wheel hub.
Right, from a simplistic view, we always view the wheel as being round, but when it's actually got the weight of the vehicle and it's going along the road, there's a flat bit at the bottom, and that flat bit can change.
That's absolutely right.
Okay.
There's certainly when we're road testing, you'll identify that when you accelerate a vehicle that you may see a T2, a second order tyre vibration. If you think about that, that tyre has changed shape under acceleration. The same as it could well do cornering, but most certainly when you brake as well, that tyre will change shape. So when you're road testing for vibration, again, it's this all-important thing about road testing with the customer under the customer's driving conditions.
Ah, this is interesting. So we've put some fabulous tuning products on this cart, producing twice the power it used to, but we've not changed the speed rating of the tyre. We accelerate under high loads, and we now have an issue which wasn't there with the original vehicle. Would that be?
That'd be absolutely right. Whenever you change wheels, tyres, suspension, and the easiest of those is tyre, the whole dynamics change. You've introduced new variables, new characteristics that the customer will interpret, especially if they've driven that vehicle for numerous miles on the previous tyres, and then they leave the workshop with a brand new set of tyres. For all intents and purposes, it's almost a different vehicle.
Yes, yes.
So the animation now, that will take us through vibration orders and hopefully bring this to life. Because here we have wheel imbalance. So the wheel is going to come off the vehicle in the workshop. We're going to balance this wheel. Important to note here that because we put 2 weights on a wheel, we don't then have 2 disturbances per revolution. Here we've applied a 10 gram and a 5 gram weight. The imbalance is in the vector sum of those 2. So an imbalanced wheel will only give us a first order vibration, and that's an important piece to remember. The more high performance, the more rigid the chassis, the more sensitive suspension components become, the more radial force variation is visible and becomes a real issue. And without that style of wheel balancing, it's a real struggle to eliminate first, second, third order tyre vibrations. A certain must consider for low profile tyres.
Also aware of the fact that when a vehicle is new, the manufacturer will identify a high spot on the rim, and the tyre manufacturer identifies a high spot on the tyre, And these, when correctly fitted, are normally set 180 degrees apart to minimise out of balance forces. And regrettably, when the vehicle ages, we no longer have that ability. So quite often, a second-hand vehicle with older rims and older tyres often does suffer from this vibration issue because of incorrectly paired
Absolutely right.
components, basically.
Yeah. And that's where, once the vehicle has come in for its first set of tyres, rim replacement, whatever it may be, to run the radial force variation, balancing on those rims, will minimise the risk of any vibration, first order or second order, by, as you said, Frank, phase matching the tyre to the rim. There is an allowance within the rim for deformation, and there is, of course, a tolerance in the tyre, and if we can match those accordingly, we can, again, minimise the risk. That's what that's about.
Yeah, sure.
So here we have the top T1, a wheel imbalance. Remember, that will give you a first order vibration. Radial force variation, again, will give you first order vibration. But be aware that could give you second order vibration. And third, this is the number of disturbances of one rotation of the wheel. An oval shaped rim, so this is a wheel out of round, yeah, generally second order vibration, often accompanied with a tremor in the steering wheel, often at low speed as well. So we've mentioned orders, we've talked about first, second and third. They are no more than the number of disturbances or shakes in one revolution. The software is designed to identify these as E for engine, P for prop shaft and T for tyre. But this is vitally important. Just because you have a T1 vibration does not mean it is a tyre. Think about other components that could be rotating at tyre speed. Drive shaft, for example, hub assembly, brake disc, differential crown wheel, anything that's rotating at tyre speed frequency.
Of course, obviously, within the workshop, brake overhaul and repairs, replacement of discs, that in itself, you replace a disc, that in itself could introduce an out-of-balance force that wasn't present prior to that work having been done.
Yeah, there's a risk of introducing a variable really by taking the wheel off the hub and then placing the wheel back on the hub in a different orientation.
Yes.
How many of us mark the wheel? I'll be honest, I don't, before I take the wheel off. We have to live in the real world. Just be aware of the numerous variables when we work on these vehicles. So what does that look like in the software? E, P and T vibrations. Well, here's the frequency view of NVH. So if you'd carried out a road test with this vehicle and you'd had a first order vibration, there it is, T1. That's a high amplitude vibration at 46 millig. That's considerable. We can see there that we've got RPM and miles per hour graphed in the signal history at the bottom. The thick black line there, that is the activity from the accelerometer. So the event in the signal history along the bottom is all live, is instantaneous, but the data in the frequency view is processed. So we process the captured data into the frequency domain.
So just to look at that from a layman's point of view, we have a large T1, a large out-of-balance event, one per rotation. We have a smaller event T2 that may not be an issue. Correct. That may be within specification. Yes. I also noticed looking at that, E1 and E2, which is related to the engine, crankshaft rotation speed, is relatively very low, almost non-existent. So we don't have an issue here with the engine. This issue is purely to do with road wheel or rotation events at the same speed as the tyre, which can include the drive shaft and the brake disc or brake drum.
It's a good point, well made, Frank, because we could quickly jump to a conclusion that great, it's a T1 vibration. Remember, it's a component rotating at tyre frequency. You mentioned there, Frank, also T2, that is a second order tyre vibration. You will find this phenomena that if you have a fundamental T1 vibration, that you will have a T2, and possibly in there somewhere is a T3, that's a third order vibration. We concentrate here on the fundamental peak, and in this scenario it is a T1, one disturbance of the wheel per revolution. Of course, you mentioned there E and P, those vibrations are low. Okay, so very quickly, coming back to what we mentioned in the first video, is confirming what is not vibrating, equally as important as confirming what is.
I think also, from my perspective, what I find very valuable from this particular series of images is that we have a very precise trace of vehicle speed and engine speed at which that event actually then occurs. So we can relate to that. If we wanted to reproduce that test drive, we can relate to that very accurately indeed.
The ability to record and analyse even the most stubborn NVH problems, and dare I say it, what NVH problem is not stubborn. If you've got the NVH kit applied to your vehicle, it's because it's a real customer complaint. It's probably fell outside the visual inspection. You can't see any problems with the vehicle, so now it's time to take an objective measurement. Remember, that would be with the Essentials kit if you don't have a scope, but if you already have a scope, then we have the starter kit, standard kit, and the advanced kit. So you do not need to purchase an Essentials kit if you already have a PicoScope. Complete out-the-box solution. Works on anything, and this is the thing, Frank, isn't it, that it works on cars, boats, trucks. If it rotates, shakes, vibrates, or make a noise,
if it moves, if it goes up and down and round, we can measure it.
You can apply NVH and diagnose. Absolutely right. Prove a fix with clear captured data. Match the speed, engine speed, road speed of the customer complaint. Capture those events. Qualify the vibrations and present the data. It may be to warranty, it could be to an engineering company that you believe a component, or you have evidence to qualify that a component is failing or is certainly generating noise or vibration. And the tool deals with the science. I think that's where we're at with the software.
Yeah, the real genius is the software. We don't have to be scientists, we don't have to be degree-holding physicists. The software takes care of the maths. We can make an informed engineering decision from this data. We've now had a look at the fundamentals of and the principles of NVH. I hope you found that as informative as I did. What we'd like to do now is to move on to the actual physical setup of the equipment, looking through the setup wizard and how we actually apply the hardware in the vehicle prior to testing.